for giving me this opportunity to present our work today. So we'll be talking about, and also the audience for joining in. So today we'll be talking about rough maximal singular integrals. This is a joint work with my thesis supervisor, Parasar Mohanty. So begin. Okay. So we start by defining the rough singular integrals. So we take omega to be a function on the d-dimensional sphere, such that the integral of omega is 0. And I define my rough singular integral.
Just 1 minute, Ankit, are you going to the next page? Because I can just see the first page.
Oh, I've gone to the next page. Can you see it now?
No.
No, it's just the title page.
Okay. Now?
Yes, now I can see, yeah.
Now it's fine?
It's okay.
Yeah, okay. So we'll start with the function omega, which is function on the d-dimensional sphere, such that the integral is 0. So we define our rough singular integrals t omega as a principal value operator with the kernel omega x omega y by mod y to the power d. So it's a convolution kernel. And it is well defined for good class of functions, let's say for CC infinity classes. Okay. So this kind of operators was first studied by Calderon and Zygmunt in 1956. So they showed that if omega is in L log L, that is the function mod omega log E plus mod omega is integrable, then this T omega extends as a bounded operator from LP to LP for P strictly between 1 and infinity. So they use the method of rotations to prove such a result. There is also another method by Duan de Cochia and Rubio de Francia, where they use a double dialectic decomposition of the kernel and the Fourier transform estimates. But they proved this result by assuming a certain stronger condition on omega, that is omega is in LQ, but their results easily extends to the general class omega in L log N. Okay. Now, if omega is Lipschitz, then this operator T omega becomes a Calderon-Zygmunt operator. And by standard Calderon-Zygmunt theory, we know that T omega is weak 1,1. So it is natural to ask if omega is in L log L, that is, we don't assume any smoothness condition on omega, then is it true that T omega is weak 1,1? Now, historically, such a result was first proved for M omega. So this M omega is a maximal averaging operator. So if omega is 1, this is nothing but our hardly retrievable maximal function, which we already know to be weak 1,1. In fact, if omega is in L infinity, then this M omega can be easily dominated by M, that is the hardly retrievable maximal function. Now, but for the general class omega in L log L, the first such result was obtained by Christ, where he showed that for dimension d equal to 2, the operator M omega is weak 1,1. Later, this was extended for all dimensions d greater than or equal to 2 by Christ and Rubio de Francia. In this paper, they also showed that T omega is weak 1,1 in R2. And this result was also independently obtained by Hoffman, where he assumed that omega is in LQ. Finally, the case d greater than or equal to 2, the for general dimensions, it was finally settled by Seeger that T omega is weak 1,1 using the microlocal analysis of the kernel, microlocal decomposition of the kernel.
So Ankit, here you are assuming that omega is in L log L, right?
Yes, omega is in L log L throughout, yes.
Okay.
Unless otherwise stated, yeah. Okay, so this is a story about T omega. Now, if we want to talk about the pointwise convergence of T omega, then by Stein's maximal principle, it is enough to talk about T omega star, the rough maximal singular integral. So which is defined as supremum over epsilon greater than 0 of the object T omega epsilon. So this is the truncated rough maximal singular integral. So this truncation is mod y greater than epsilon in the kernel. So by using the method of Calderon and Zygmunt, that is the method of rotations, or by double diagonal decomposition, it is easy to show that T omega star is LP bounded for P strictly between 1 and infinity. So what about the case for P equal to 1? Is this operator T omega star weak 1, 1? Actually, it is a long-standing open problem, and it's still not known whether T omega star is weak 1, 1 even for omega in L infinity. So if we don't have such a result, what better can we expect? What we can instead do is we can make our domain smaller and expect some weak type result. So this is what is there. It is standard that for a unit cube Q in RD, this operator T omega star is from L log L of cube to L1 infinity. Recently, in 2020, Honzik proved a better result. So what he showed was, if omega is in L infinity and integral of omega is 0, then for epsilon greater than 0, the operator T omega star is bounded from the space L log L 2 plus epsilon to L1 infinity locally. And the bounds depend on this epsilon. So this space L log L 2 plus epsilon is certainly bigger than L log L, which was the previous known result. Now, it is natural to ask that, can we do better? So, can we improve this result? So the first question that we can ask is, can we make this domain larger? So can we drop this 2 plus epsilon? Can we get a result like L log L, which is a bigger class than L log L 2 plus epsilon? The other thing we can ask is, here Honzik assumed that omega is L infinity. So can we generalize this for omega in L log L? And thirdly, we can ask that whether we can have a global result instead of a local result. Okay, so this is the questions that we want to answer. So we have our result, which says that if omega is in L log L, integral of omega is 0, then T omega star is of weak type L log L. That is, if I take any alpha greater than 0, then the distribution function of T omega star at alpha, the measure of that is dominated by 1 by alpha times the L log L norm of mod f. Okay. So this is our result. So we would like to talk about what were some of the inefficiencies in the earlier proofs. So the first was, if we apply Honzik's method to the operator T omega, the rough singular integral operator, then it yields L log L 1 plus epsilon to L1 infinity. But by the result of Seeger, we know that this operator is bounded from L1 to L1 infinity. So using this method, we get this extra 1 plus epsilon part. This is because Honzik uses the Orlick's type averages instead of the natural L1 averages. So therefore, that restricts his class of domain. Secondly, he also employs the double dyadic decomposition, which was used by Hutinen, Roncal, and Tapiula to get some weighted estimates on T omega. And he also relies very much on the size of F uniformly. So instead, what we will do is, we will break our functions into finer pieces based on its size. And we will delay the double dyadic decomposition to a later stage. Okay. So what we will do is we will employ the decomposition of Seeger, Tau, and Wright. So they used such a decomposition to prove the similar L log L estimates for certain radial transforms. So we begin with the proof. Okay, so far any questions? If not, then I'll proceed. Okay, so I'll proceed. So we'll begin by discretizing the supremum. The supremum is for the T omega star is over epsilon greater than 0. So what we'll do is we'll take a smooth compactly supported function beta, which is supported on the annulus, and such that summation of beta I is 1 for x not equal to 0. Where beta I are the dilates of beta, that is beta ix is beta to the power minus ix. And we will have an inequality, will dominate our operator T omega star by m omega plus a discrete version of the rough singular integral. So instead of epsilon greater than 0, we have k greater than 0, and the sum is over different scales of the kernel ki, such that the ki is k times beta I, and k is our kernel omega x by mod x by mod x to the power d. Okay, so we would like to see a short proof of this inequality. So just to see that, to get such an estimate, what we need is we need to get hold of T omega epsilon. So for an epsilon fixed, we will choose k epsilon to be greatest integer function less than equal to log 2 plus epsilon. So with this k epsilon, using the truncated kernel support condition, what we can get is T omega is dominated by the positive operator kk epsilon mod kk epsilon convolved with mod f plus the discretized summation I greater than k epsilon ki convolution f. This kernel kk epsilon lies between an annulus. So it's a good function. So it can be dominated by m omega, because this k has omega inside it. So this is the reason we get m omega. Plus, now if we take supremum over this epsilon, over all epsilons, we will get the corresponding, we'll get the result that what we need, the discretized version of the rough singular maximal operator. Okay. So this is the proof for this inequality. And what one can see is that we already know that m omega is weak on 1 by the result of Christ and Rubio de Francia. So therefore, it remains to estimate this operator, this discretized rough singular operator. So to do that, we begin with the function f in L log L and an height alpha greater than 0.
Yeah, Ankit, your k is omega here, no? Omega divided by.
So k is omega x by mod x divided by mod x to the power d. Right?
Okay.
Okay. So by a stopping time argument, we can choose a maximal collection f of dyadic cubes such that the average of f over the cube in the collection is greater than alpha. Now, since this is a maximal collection and the parent of f is not in the collection, therefore we will get this second inequality for free. That is, the average is less than 2 to the power d times alpha. And we can take out the exceptional set E as in the standard Caldera-Zigman theory. That is the union of scales of cube. So 100D cube means the cube of with the same center as cube and side length 100D times the length of cube. So the Lebesgue measure of E is easy to calculate. It is nothing but summation mod q, and with this first inequality, this mod q is less than 1 by alpha times the norm of f. So we get the estimate for the exceptional set E. Now for the function f, we decompose our function f into two parts, the good part g and the bad parts f cube, which are supported on the cube's cube. So what we do is, this good part is nothing but f restricted to the complements of the cube in our collection, plus f restricted to the range where mod f, where the size of f is less than some constant times alpha. And the fq is the remaining portion, f restricted to q intersection with the size, the range where the size is greater than the constant times alpha. So it is easy to see that mod g is less than equal to alpha, because this first part is dominated by some constant times alpha by Lebesgue differentiation theorem, and this part by definition is less than alpha. So hence g is an L infinity function bounded by with the operator norm less than equal to alpha, and the norm of the L1 norm of g is less than the L1 norm of f. So hence g is also in L2 as it is in L infinity and L1, with the L2 norm less than equal to alpha times 1 norm of f. So g is a good function in this respect. Okay. So for the bad part, for fq's, what we do is we further subdivide this fq's into final pieces fqn's based on the size of fq's. So what we do is fqn is nothing but fq restricted to the annulus 2 to the power some constant times 2 to the power n minus 1 and 2 to the power n times alpha. So heuristically one can see is that this we have twice exponential, like 2 to the power n in the picture. So this number of 2 to the powers actually determines which domain we will get. So there are 2 to the power, so we get L log L. So number of logs, it determines the number of logs. Okay. So this is fqn. Now, as in the standard Calderon-Zigmund decomposition, we break our fqn into gqn plus bqn, where gqn is the average on the points where on the points in the cube, and bqn is nothing but fqn minus gqn. So the support of bqn is contained in the cube, and also the integral of bqn is 0. Just by integrating we can see that. Okay. So now for each n, we collect cubes with the same size n. So this gn is summation q gqn, pn is summation q bqns, and similarly fn is summation q fqns. Okay. So we will see some properties of this smaller functions which are easy to deduce once we have a piece of paper and a pen. So the first one is the L2 norm of fqn of fn's is less than 2 to the power c1 to the power n alpha times f1 norm 1 norm of f. So this follows by the condition on the size. It follows by the second inequality. The second property is, which we have already discussed, that integral of bqn is 0. The third one is the L infinity norm of sums of gqn is dominated by some constant times alpha. To see this, what we can see by the definition of gqn, if I take summation in n, this summation in n goes inside this integral, and summation in n, fqn is nothing but fq. So this is 1 by mod q integral of fq, which is nothing but the average of fq. So that is less than equal to alpha. And since these q's are disjoint, so the summation in q sums up pretty well, and this leaves us nothing but alpha. Also, the L1 norms of the sums of gqn's and bqn's are bounded by fqn's, that is by definition. And since since fqn's are disjoint for each n and q, so this sums up and gives us the L1 norm of f. Okay. So this gqn, summations of gqn's, they are in L infinity and they are also in L1. So they will also be in L2 with the norm L2 square, L2 norm squared will be less than equal to alpha times L1 norm of f. So this GQNs are also good functions in that. They are in L2 with proper control. Okay. So once we have the decomposition of the function, we will proceed to the decomposition of the kernel. So I think it's quite handful of symbols here. So just to revise, we have our F, we break it into G plus FQs, and then we further break our FQs into FQNs. Okay. So for the kernel, what we do is we take a good CC infinity function phi, which is supported in a ball of radius half, centered at origin, and it is normalized to give integral of phase 1. So what we do is we smoothen our kernel Ki by convolving it with dilates of phi. So K0i is Ki convolution phi minus I, and Kni is Ki convolution phi 2 to the power n minus I. And this phi j's are the L1 dilates of phi. Now we need to estimate this level set, that is the discretized supremum that we deduced earlier outside the exceptional set. So what we do is we look at this kernel and expand our F into G plus summation over n fn's. Now in the second term, we add and subtract the smoothened kernels K0i and Kni, and we get two more terms, Ki minus Kni convolution with F, Kni minus K0i convolution with Fn's, and K0i convolution with Fn. Okay. For the third term, what we do is we expand this Fn into Gn plus Bn. So we have one more term. So we have 3 terms. So we have 5 terms in total. We will name them. So the first 3 terms are the good parts, which we call them as HK1, 2, 3. The fourth term is HKCZ, and the fifth term is the bad part, HKB. So we look at the estimates of the good functions first. So to estimate the first 3 good parts, what we will show that is the supremum over K, HKJs, L2 norm is dominated by alpha times the L1 norm. Once we have that, then for the level set of this operator, we can just use the Chebyshev's inequality and this L2 inequality to get it to get the level set to be dominated by 1 by alpha times norm of one norm of F. So it's standard. So we just need to prove such an inequality. So we prove.
Ankit, could you recall what is Fn?
Yeah. So yeah, So Fn is summation over all the cubes in our collection, FQNs.
Yeah, fine.
Okay.
Thanks.
Yeah. Okay, so we'll prove such an inequality for the first term. So for the first term, it actually follows by the L2 boundariness of T omega star. So this was proved by Duan, Dicochi, and Rubio di Francia. So what they essentially showed that the supremum over K of this kernel is an L2 operator. And so we have this first inequality. And then we know that G is a good part, and we have already calculated its L2 norm, which is less than alpha times 1 norm of F. So we have such an inequality for the first term. For the second and third term, we will need certain L2 estimates for the intermediary operators. Namely, what we will need is such an estimate. So this estimate, first, it was, this estimate has been used by Diplinio, Huthenen, and Lee to prove certain sparse domination for T omega star. So we'll be using this result. So what it says is that the intermediary operators KMI minus KM minus 1I convolve with F, and if I take the supremum over all case, then it's L2 bounded with the L2 norm having the decay 2 to the power minus 2 to the power m. So this decay is very important because we need to sum up all the sums in M. So what we do is once we have this lemma, we can expand the second term ki minus kni telescopically as m from n plus 1 to infinity, and this intermediary operators that we see here. So we can just take the L2 norm, and since we have a decay in m, this sums up pretty well. And by the properties of the function fn, this also sums up. So we get the inequality, desired inequality for the second term. The third term is similar. We expand kni minus k0i again telescopically into this intermediary operators and use this lemma to be the desired estimate. And we know that Gn are good parts, and we have already calculated that the L2 norm of Gn's are well behaved. Okay, so far so good. So this is
Decay come here.
yeah.
This decay, how from where this decay is coming? Is
Which
2 to
one?
the power minus 2 to the power m.
Yeah. So
This-
this decay is actually coming from here. So this KIM is nothing but Ki convolution with phi of 2 to the power m minus I, right? So using the Fourier transform estimates and the double dielectric decomposition, we get such a decay.
Okay.
So this ki hat of zeta is actually satisfies the estimate minimum of 2 to the power I zeta to the power alpha and 2 to the power I zeta minus alpha. So using that Fourier transform estimate, one can get such a decay. So this convolution with phi m is important, phi 2 to the power m minus I. So this gives such a decay.
Okay.
Okay. So this is a story about the good parts.
And do you, for L2, you apply Plancherel? I mean, you dominate it by the square sum? Or?
Yeah. For L2, we apply the Plancherel. Actually, we use a double dielectric decomposition. Like first, we take the partition of unity, and then we use a little bit Bailey argument, like it was done by Duhan-Dicochi and Rubio di Francia. And using the Fourier transform estimates, we get such an inequality.
Okay.
So Fourier transform estimates are the key here. Okay. So for the fourth term, what one can observe is this summation I k0i is a Caldern-Zigmund kernel, because this k0i is nothing but ki convolution with phi of minus I. So this convolution smoothens the kernel out, so it satisfies the growth and Hormander conditions of the Caldern-Zigmund theory. So they are standard Caldern-Zigmund kernels, and thus this supremum of this term behaves very much like the maximally truncated Caldern-Zigmund operator, which is known to be weak 1-1. Hence, we have the first inequality. And by summing in n, we get this to be dominated. The L1 norm is dominated by the L1 norm of F. Okay. So this is about the Caldern-Zigmund term. Now it remains to show the estimates for the back part. So any questions till now? I mean, you want me to revise something on? Fine. If no, then I'll proceed. Okay. So we have to estimate the bad part, supremum over k, and this discretized sum over outside the exceptional set. So like in the arguments of Christ, Rubio di Francia, and Seeger, we first collect cubes of same scales. That is, we write our Bn, the bad part, as summation over S, Bsn. This Bsn is nothing but we collect all the BQNs such that the length of the cube is 2 to the power S. So therefore this Bsn. So we are collecting cubes of the same length. Now, the support of Kni is contained in the annulus 2 to the power I minus 2 and 2 to the power I plus 2 for all n. So hence, using the support condition of the convolutions, one can see that for S less than 3, this convolution with the bad part is 0 outside the exceptional set. So hence, we need to only worry about S greater than or equal to 3. Okay, so we need to estimate this level set. Okay. To estimate this level set, first what we'll do is we'll reduce our problem Okay. So we'll reduce our problem to some, we can take care of some finitely many scales S and the infinite scales. So for the finitely many scales from S between 3 to Cn, what we do is we use the Chebyshev inequality and we just put the L1 norm inside. And this, so this supremum K, I greater than K is dominated by summation over all I in Z because everything is positive. And using that, the L1 norm of Kni is dominated by the L1 norm of Ki times the L1 norm of Ci, but L1 norm of Ci is 1. So the L1 norm of Ki is dominated by the L1 norm of omega. So therefore, this term is dominated by some constant independent of n. And by definition, Bi minus n L1 norm is less than the summation over all cubes of BQ, L1 norms of BQs. And if we sum this I and Q, so that is we collect all the cubes in our collection, we get the summation over Q in the collection F. And this BQN L1 norms we have seen is dominated by the L1 norm of FQNs. So now this part is independent of S. So we can just count the number of S. And so we have n many S's here, Cn many S's. So we just put an n here. And now using the definition of FQN, we know that FQN is equivalent to 2 to the power C1 times 2 to the power n alpha. So if I take log twice here, so log FQN, I get n here. So this is what is, so n is dominated by log E square plus FQN by alpha. So this is how this 2 to the power determines the number of logs in our story. So once I have this, then just by summing in Q and N, since FQNs have disjoint support, this is nothing but the L1 norm of F, the L log N norm of F. So this is how we take care of finitely many scales. Now it remains to show this for infinitely many scales, that is S bigger than Cn. So for S bigger than Cn, what we do first is we reduce our problem from omega in L log L to omega in L infinity. So to do that, what we do is for delta greater than 0, we define a set of points in the sphere such that this mod omega is bounded by 2 to the power delta S. So this is just like the bounded part of omega. So what we do is we break our omega into an integrable part and a bounded part. So this integrable part is the part of omega which is outside the set, and the bounded part is the part which is bounded by 2 to the power delta S. So we call that integrable part as omega plus and the bounded part is omega minus. So once we break this kernel into two parts, omega, since our kernels k and i's also depend on omega, they also break into two parts, k and I plus and k and I minus. So this k and I plus minus is by definition ki plus minus convolution with phi of 2 to the power n minus I, where this ki plus minus is nothing but our kernel, but omega is replaced by omega plus or omega minus. So hence this level set that we want to estimate decomposes into two parts, one with kni plus and the other with kni minus. The first one we call it B plus, the second one is B minus. So for the estimate of B plus, we use Chebyshev inequality and we push the L1 norm inside as before. So the supremum goes away and what we are left with summation over I in all of Z. And we know that, and just taking the L1 norm inside, we get this. So this Ki plus L1 norm is, so this is the integrable part such that the omega is greater than 2 to the power delta S. So this is dominated by the integral over ds complement of omega. And this bi minus Sn is dominated by bqns. So next what we do is we push this sum, S sum inside the integral by your application of Fubini. And we get the cardinality of all S, which is such that 2 to the power delta S is less than the mod of omega by 1 norm of omega. That is by definition. So we just count this by taking a log here. We can see that the cardinality is less than log times mod omega by norm 1 of omega, L1 norm of omega. So hence we get, for this, instead of this, we get the L log L norm of omega. So this is the part where we use the L log L condition for omega. And our problem is basically reduced to just the part where omega is in L infinity. So that is the part B minus. Okay. So for B minus, what we do is we look at the kernel. The kernel is K and I minus K0 I minus. We again expand this kernel telescopically, right, from M from 1 to N, and we call each intermediary pieces HMI. Now, this each pieces, that is, this HMI is supported in an annulus of dimensions 2 to the power I minus 2 and 2 to the power I plus 2. And for each n, the derivatives of HMIs, they satisfy an estimate, a uniform estimate of 2 to the power delta S, which is uniform in theta, R, and M. Okay. So this one can see by brute force and just differentiating and using integration by parts. So once we have the estimates of Seeger, we will follow the microlocal decomposition, which he employed to prove the weak 1-1 boundedness of the rough singular integral T omega. So what we do is we break our operator, intermediary operators, HMI into gamma MSI plus HMI minus gamma MSI. So by Fourier transform estimates, actually these are the two lemmas of Seeger. So for the first part, we have an L2 estimate. The kernel KMSI convolved with the back part. This L2 norm is dominated by this decay factor in S. So this decay is very important because we need to sum an infinite sum in S. So this decay is what we need, 2 to the power minus delta S times the alpha times alpha and summation over the L1 norms of BQs. For the second term, we have a better L1 estimate with same growth factor, 2 to the power minus delta S. So once we have Seeger's decomposition, we have a certain idea on how to sum the S part, but still we have a supremum sitting inside. Supremum in K sitting inside the definition of T omega star. So to deal with such maximal operators, we need certain Kotler type inequalities. So what it says is that we have a sequence of non-negative functions Vi such that the L1 norms of Vi are uniformly bounded. Then such a pointwise inequality hold. So for this intermediary operator, the supremum over K and summation I greater than K, HMI convolution with the back part. So that is dominated by sums of the composition of Hardy-Littlewood maximal function of this rough singular operators HMI convolution with Bi minus S of N. So this actually behaves like the rough singular operator T omega. Just the index set is different. So that in Seeger's lemma, we mentioned that this estimate holds for any index set I in Z. So hence we have this different index sets. So this is basically by Euclid's algorithm that if I divide I by S to the power n plus 2, then the remainder is R. So I collect all such I's. So this is the kernel here. Plus certain operators which are convolution with an L1 kernel. So these are pretty nice operators. And we also have nice decay here. Actually, we have a decay of 2 to the power minus delta S here sitting inside. So this helps us to sum up things. So if we recall the Kotler type inequality for Calderon-Zigman operators, so it says that T Cz star is dominated by the maximal function times maximal function of T Cz plus some maximal function. So this inequality is very much similar in that spirit. So we have this M of the operator T omega plus some integrable operator. So now once I have the Kotler inequality, so it remains to show that I have to estimate B minus the level set with the kernel Kn I minus minus K0 I minus. So I telescopically expand this kernel into M from 1 to N HMIs. Each HMIs are Seeger type kernels. So what I do is I have this M and N sum. I apply a Fubini and exchange the sums here. So it gives me sum in M and sum from N from M to infinity. And then I pull these three sums outside the supremum to get this. Okay, so I need to estimate this thing. But by Kotler's inequality, I can estimate this sum, this term, pointwise by these two terms. So this level set is dominated by these two sums, these two parts. So the first part is the integrable part. So what to estimate this, what we do is we apply a Chebyshev's inequality. So I get 1 by alpha times the norm of this L1 norm of this complete thing. I push the L1 norms inside. So this is uniformly bounded in L1. So this is taken care of. So here it remains the L1 norm of BQNs. And I already have a sum in, I already have a decay in S. So I just put the decay, I use the decay of S from Cn to infinity. So what it happens is if I take C to be very large, let's say 10 crores. So this is pretty huge decay in S. So this decay in S gives me decay in N when I sum this. So then I have 2 to the power minus N. And then when I sum this gives me decay in M. So 2 to the power minus M. So which further makes this sum summable. So hence I have my result. For the second term, what we do is we use the decomposition of Seeger and we break our kernel HMI into two pieces, into two microlocal pieces here. So for the first term, we similarly apply the Chebyshev's inequality with one norm, and we use the positivity of the maximal function M and its weak 1-1 boundedness. So we get the L1 norm of this thing. But by the estimate of Seeger, the L1 norm of this thing has a decay of 2 to the power minus S. So again, the same story goes. This S gives me the decay in N, this N gives me the decay in M, and this makes the thing summable. For this part, I use the Chebyshev's inequality with the exponent 2. And by the L2 boundedness of the Hardy-Littlewood maximal function M, I am left with the L2 boundedness of this kernel. And the estimates of Seeger again gives me the L2 norm of this kernel is dominated by 2 to the power minus delta S. And it's the same story again, everything sums up pretty well. And it gives the bound for B minus. And this concludes the proof of our result. So yeah, I'm done. So here are some of the references for this talk. So it's 4:17, right on time. Okay, that's good. Okay, so here are some of the references. Okay, and I thank the audience for the patience and for attending this lecture. So anyone has any doubts, questions, or queries or suggestions, they can feel free to discuss. Okay, thank you.
Thank you, Ankit, for a really nice talk. So are there any questions?
Hi, Ankit.
Yeah.
So here in the proof that omega is in L log L, this was used in this estimation of the B plus, correct?
Yeah, in the B plus.
Do we also use it elsewhere somewhere?
Which one? Can you come again? So
I mean, is it also used at some other place?
no, the L log L condition is only used for B plus.
Okay.
Yeah, like you said, yes.
Okay.
Yeah.
It's quite technical.
Yeah. I know. Yeah, so the L log L condition is only used for the finitely many scales. This on the function, the condition on the function is used here, and on the omega is L log L is used only for B plus.
All right.
Yeah.
Oh, thank you.
And the open problem which you said in the beginning. So for some classes, it's proved, right, that it's weak bounded, this T omega star.
For omega, you mean?
Yeah, for omega in some class, is it?
For if omega is Lipschitz, then we know that T omega star is a maximally truncated Kalle-Newman operator. So we know the weak boundedness for that. I mean,
Okay.
But if you want no smoothness condition on omega, just the size condition, that is omega is L infinity, then it's still an open problem.
Okay.
Yeah.
And then this is, so what you have is that omega, when omega is in L log L, you have weak bounded from L log L, right?
Yes, from the Aldrich space L log L to L1
But from
infinity.
L1 to L1 infinity, weak bounded for this kind of function.
For which kind of functions? But I mean, that is not, that is still an open problem, right?
Yeah, of course. Okay.
I didn't get
For
you.
some functions, I'm saying that, like you said, for Lipschitz functions, of course, it is known, right?
Yeah, for omega in Lipschitz, this is known. Yeah, with some smoothness condition, it is known. But just the size condition. So that's still an open problem.
Okay. And if we just replace omega in L1 instead of L log L, so does that make any difference? That does, of course, but
yeah. So L1 is a pretty huge class. In fact, it is not true that if I take omega in L1, then it is not even an LP operator, LP bounded operator.
okay.
So what is known that if omega is in H1, the Hardy space on the sphere,
Okay.
which is smaller than L1, then it is LP bounded. But the weak one isn't still an open problem for such a class.
And are there some applications of this theorem which you have proved for particular known, rough singular integral operators?
So this is a result in itself. I mean,
yes, sure. No, I'm just saying that all these problems like spherical maximal or Bochner-Ries.
So this method can be certainly employed, and actually for discrete spherical maximal function, Seeger tau and Wright has already proved that the discrete spherical maximal function is bounded from the Aldrich space L log L to L1 infinity. That is known. Yeah.
Ankit here, so that result is known, right? If omega is in L infinity and the average is 0, then it is weak type 1,1.
Which one? Then T omega is weak type 1,1.
No, T omega star.
No, that is not known.
Okay.
That is an open problem.
You're saying it's an open problem.
Okay, just go back to your previous slide.
Yeah. This
I
one?
think that result of Honjit.
Honjit.
Okay. Okay.
This one is log L2 plus epsilon.
Yeah.
This is a smaller class than L1.
Yes.
Much.
Yeah, but I think sometimes it does give interesting results for all those operators, like Buckner-Rees at the critical index. I think you can perhaps
Yeah, for the critical
as a
index,
corollary or something. Yeah.
yeah, we already have a result for the critical index. I mean, it's there in our paper. So
I see. So can you
Yeah.
state that here? Is
yeah.
it here?
So the critical index falls under a bigger class of H omega. So so for the critical index, what we have is this omega is 1, and we have an H. So what is that H? H is basically cos of 2 pi mod x, right?
Mhm.
Yeah. So for those class of operators, we have the same result for this maximal function.
Same result as in your result, not this Hanzik's, right?
Yeah, our result. Sorry,
Yes. Yes.
Yeah.
Okay.
this result. But that is not the maximal Bochner-Rees operator. That is standard. It is the maximally truncated Bochner-Rees operator.
Mhm.
Yeah.
So the truncated means you truncate the kernel.
Yeah, you truncate the kernel and then you take the supremum over all epsilons.
Okay.
Yeah.
Mhm.
Yeah, so we also have a weak type inequality for this T omega star, weighted weak type inequality, but that's a story for another time.
Okay. So are there any more questions? If not, then let's thank the speaker.
What about weighted, you said?
Sorry, I'm sorry. Yeah,
Okay.
please.
Yeah.
You said some weighted result, I just missed it.
Okay.
Some weighted result you just said.
Yeah. So if the weight is A1, like Makarov T1 class, then this results hold for this weight. So the the
Weak type weighted.
the weak type weighted result, like right, the A1 result that we have.
Okay.
And we
That
also
also
have,
you have proved
huh?
in this paper.
Yeah.
This result you have proved in this paper.
Yes, yeah. And we also the weight constants also we have calculated, and that matches with T omega.
That is also sharp, the constant.
That is known sharp, not sharp. Even for T omega,
Okay.
it is not known whether the exponents are sharp or not.
Yeah.
Yeah.
Okay. Yeah. Any more questions? I think Sanjay has a question. He put it in the chat.
Okay. Let me see. yes, it is.
Yeah. Okay, let's, you can unmute and clap. Yeah. I'll stop the recording.